So let's talk about lighting. Lighting is of course a generally huge topic in computer graphics, and it's still very much being deeply researched and is constantly advancing. You've probably heard of modern techniques like ray tracing and PBR, so physically based rendering, and microfacets and stuff. But I think for a beginner it's very important to understand the basics, so we'll start with that. And being a beginner myself, I found quite a lot of material on how to implement some basic shading, like the font light, for example, named after Dr. Buitong Fong. And there's also a lot of material on physics and like color theory and stuff. However, I haven't found a whole lot of material that goes deep enough without being too nerdy, and so still being practical for a beginner graphics programmer, because that's what we're after here, right? But thankfully, I found this amazing lecture by Professor Thorsten Thormeilen from the University of Marburg, and it starts with the most important bits of theory about colors and light in general, and then it proceeds with actual math behind it, and ends with the actual shader implementation of font lighting. And I can only recommend you guys spending an hour and watching it with full focus. And I actually watched it a couple of times, and while I won't pretend that I understood everything, I think I've got enough to proceed with actual coding. So I'll start with that, and I'll try to explain everything in layman terms, and yeah, I'll try to do this as best as I can. So also I've decided to change the format a little bit and do less live coding, and actually even write a script for this video, so I can just hopefully be a bit more concise and not spend a lot of your time typing stuff and making stupid typos and whatnot. So let's start. Before we do anything, let's actually set our clear color to 0, so it's black and doesn't distract us from other colors. So let's take a look at our current fragment shader. It simply samples the color value from the texture and returns us back to the pipeline. And let's actually remove it all and start from scratch, because even though we are implementing a pretty basic lighting, it still takes its root from real physics, so we are gonna talk in different terms. First, it might make sense to think about what light and color even are. Well, light is an electromagnetic wave, right? And humans perceive waves of specific wavelengths as different colors. But we, of course, don't really work with wavelengths here, right? But rather with a kind of abstraction that represents the light as values from 0 to 1 in these R, G, and B channels. And you should totally watch the lecture if you want to know how that maps to real-world light. But the nice thing is that we can apply our shading math to each of those values the exact same way at the same time, using the handy shader types like float 3 and float 4. So let's take a look at this math. The base for all of it is this rendering equation. Now it might look intimidating, but it's really not that bad. It mentions the term radiance a lot, which can simply be described as light going from some surface into some direction. That's basically it. Now, when it comes to drawing pretty pictures on the screen, we are mainly interested in the radiance that is going from the fragment that we are currently drawing in the fragment shader into our eye, right? So in this fragment shader, we are treating the fragment as a tiny surface that radiates some light into our view. And we want to calculate this radiation value in this RGB format for each of the channel. So looking at this rendering equation, I've wrote some hint here that the outgoing radiance is a sum of emitted radiance and the reflected radiance, right? And the emitted radiance is something that is produced by the surface itself, as if it was a lamp or a screen or something like that. And the reflected radiance is actually produced by other surfaces like the lights or something, and is reflected by our surface. And our surface in this case is the fragment that we are working on. So let's just type this out in our shader exactly using the float 3, so we can work with all 3 channels in parallel, right? And let's directly return that from our shader as float 4 with the alpha value of 1. Now we can say that our emitted radiance is full red and no green and blue, and our reflected radiance is non-existent. And you probably guessed it, if we run our program we'll see that the shapes of our objects are in the same red color. And this is because each fragment of their surfaces radiate the same light towards the viewer, so it makes sense. Now, actually, if we remember how we sampled the value from the texture before and simply return it, in this model it would be as if our object emitted that light directly, even though our cars are supposed to be made of metal, right? And really only reflect the light. So let's continue decoding the reflection part of the formula, this one. We can ignore all the integration stuff, so there are just two factors in it, the irradiance and something called BRDF. And before going further, let's just type that out in the shader. So reflected radiance is irradiance multiplied by BRDF. Now let's start with the easier part, irradiance. For us, that's just a fancy word for the radiance received by the surface, so basically how much light is received by our fragment. And that depends on two factors here. The incoming radiance, which is basically just light coming from somewhere, and the angle of incidence, which describes how the light ray hits our surface, and is basically the angle between the direction from our surface to the light and the normal of our surface. And we use the cosine of this angle to weaken the irradiance based on how much the surface is facing the light. So let's type that out as well. Now the incidence factor, since it's just a cosine of two directions, which are of course vectors of length 1, we can simply use the dot product. And actually I don't think this comment is helpful anymore, so let's remove it. So the value of 1 means that the angle between surface normal and the direction to light is 0, and the cosine is 1, so that would mean direct incidence, and 0 would be that the surface and the light ray is kind of parallel, so there's no incident at all, and anything less than 0, so like -1, that means that the light is coming from the other side, so maybe we should calculate the reflected radiance only if the incidence angle factor is greater than 0. Something like this, right? The reflected radiance is only calculated if the incidence factor is greater than 0. Now, BRDF here stands for bidirectional reflection distribution function, and in simple terms it is the function that calculates how much the radiance is reflected by the surface material. It's called bidirectional because it takes into account both directions of light. The incoming one, so from the light source to the surface, and the outgoing one, so back from the surface into our eye. And this is where the magic happens, and different materials can display different behaviors. And there are a lot of different BRDFs, taking different parameters and producing different results. And for this video we are gonna use the Blin-Phong BRDF. It might not be the best one, but it's very simple to implement and gives a pretty nice visuals. Blin and Phong are of course names of the researchers, so Bui Tuong Phong proposed his reflection model and later Jim Blin improved it. For now we are gonna set the BRDF value to 1, because we still have to do some work to calculate the irradiance. And the value of 1 basically means that all the irradiance is being reflected into the direction of view without any change, right? So let's continue with irradiance, as we still have quite a lot of undefined variables here, like the incoming radiance, or the direction to light and the surface normal. And the incoming radiance is just the light that is coming from the light source. And for our case we can simply define it as the light color, maybe with some intensity multiplier, and depending on the type of light we might also want to apply a weakening factor based on the distance to our fragment, commonly called attenuation. Of course we could go further with real physics and talk in the terms of energy and such, but often games just stop here and just define some variables that the artist can change. So let's define light color and intensity. Let's just hardcode it for now. So we have a light source that emits on all the channels, so basically just light. And I just realized that we are actually calculating the irradiance after we're using it, so let's move it up. And a good and simple way to model attenuation is to divide the irradiance by the square distance to the light. Or alternatively, we can just calculate the attenuation factor as 1 divided by the square distance. And now we simply multiply the irradiance by it. This is good enough, but without physically based rendering, you actually often want to have a more fine-grained control over the attenuation, so people often add some variables to this formula to better control how it scales with the distance. Let's not do it now, but add a to-do. So the incoming irradiance is just the light color multiplied by the light intensity. Now we're just missing the distance and the direction to the light and the surface normal. The distance and direction to the light could easily be calculated if we knew the positions of the light and the fragment, right? And the light position is something that we can hardcode for now next to its color, so let's type that out. Let's place the light a bit to the top, right and back, like 333 in world coordinates. And the world position of the fragment could be provided as another input variable, interpolated between vertices by the rasterizer. So let's add that to the input structure and pass it from the vertex shader. So now we can simply calculate the vector to the light by subtracting the light position from the fragment position. Then we can get the distance with the length function. And finally calculate the normalized direction by dividing the vector by the distance. So now we are just missing the surface normal, and the surface normal is something that is normally provided by the mesh. So as far as the fragment shader is concerned, that would be just another input variable. So let's type that out. And maybe one thing to remember here is that if we provide that from the vertex shader, that is gonna be interpolated between fragments, and the interpolation doesn't really guarantee that the normal stays a unit length, so the length of 1, which means that we should probably normalize what we get. So let's do exactly that. And finally, the incidence angle factor is of course just float and not float 3, because this is just a cosine. Now this is it for the fragment shader for now, and let's work on actually passing those values from the vertex shader and ultimately from the game code itself. Alright, our vertex shader actually outputs the position as a system value position, right? But this is a clip space position and not the world position that our fragment shader needs. So maybe let's rename this to clip position and add the fields that are expected by the fragment shader. So to calculate the position, we need to basically just have the input position multiplied by the model matrix and not the view and projection matrix. The problem is that we currently have MVP as a pre-multiplied matrix, so we basically want to split this into maybe VP and M. You could also split it in 3, but let's keep it with 2 for now. Something like this. And by the way, one thing to notice here is that the view and projection matrices, they are the same for all the objects in the render frame, because we are rendering the whole frame from the same viewpoint. While the model matrix is different for each object, right? So it would be nice to actually only push the VP matrices to the GPU once and only push the model matrix for each vertex. We can do this later, let's add a to-do for that. I just say separate global and local UBOs because the VP would be a global uniform and M would be a local one. Now we can quickly do the same in our game file, change it in the type, and change it here in the render function. Let's go back to our vertex shader and calculate the vertex world position. We do it exactly the same by multiplying the matrix with a homogeneous float 4 coordinate, but using M instead of MVP. Now we can calculate our clip position by multiplying VP with the world position and specifying the XYZ parts of the calculated world position as the output field. And by the way, if you will try to run the application now with the Direct3D 12 backend, you will get this error that the graphics pipeline couldn't be created, the parameter is incorrect. And this actually has to do with how shader cross works. So if we take a look at our fragment shader currently, you notice that we are currently not using the color and the UV input fields. And the shader cross compiler tries to be smart and eliminates these fields. We can actually, for example, check the metal output to see that it only has the text core 2 and 3. And this is something that the Direct3D12 backend doesn't like at all, because it expects the text cores to start at 0 and go in sequence. Vulkan, on the other hand, doesn't seem to mind too much. So let's actually re-enable the SPERV shader format and thus the Vulkan backend, because it also has this nice validation layer that will provide us with useful messages if we do something wrong. Now, it actually does provide us with a useful message saying that the fragment shader wants an input at location 3, which is our normal, but it's not declared as the output in the vertex shader, because it was again eliminated as not used by shader cross. So let's actually provide the normal. And as I mentioned before, normal is something that should come from the mesh, so that should actually be part of our vertex data that is fed to the vertex shader. So let's define it as the input, the next text chord field, and now we need to provide it as an output. Now there's some nuance with how we should provide the normal shader, because the fragment shader expects normals to be also in the world space, while the input is of course in the model space. So we need to convert it to the world space. However, the normal is a direction vector, so it should start at 0 basically, right? And it shouldn't be translated by the model translation matrix. Thankfully, that is pretty easy to do, thanks to the 4-component homogeneous vectors that can be multiplied with our matrices. So if we specify 0 instead of 1 as a W component, the translation will not be applied, which is exactly what we want. So let's do that. Then we want to convert it to the float 3, so only take the XYZ part. And finally we want to normalize it, as we want to actually pass the unit direction vector. And actually this is still not fully correct, because this will only work if the model has a uniform scaling. If it has a non-uniform scaling, that is, it scales non-uniformly across different axes, the normal will be incorrect. There is this article describing the problem here, that the normals are not reflecting the actual shape of the ellipse, like here, and this is something that can be quite easily fixed by introducing a normal matrix, but let's not do this now, because we don't have scaling at all, let alone non-uniform scaling. But let's add a to-do to come back to this later. And now we just need to provide the normal information for the mesh through the vertex buffer, right? But before doing that, I've actually noticed some mistakes that I made, and let's fix them before proceeding. And the first mistake is right there. Of course, we need to pass the normal and not the position here. So let's change that. And then there are some issues in the shader fragment, and because the vector to the light should be a subtraction of our fragment position from the light position, right? Because it's always subtraction of the beginning from the end, right? So let's invert that. And the third issue is that I somehow lost this multiplication on the attenuation factor here. So let's add it back. And then there is one more thing, that we are still using the emitted radiance of red that we will not want to see when we are working with our reflection further. So let's change that to 0. Now, the last missing part before we finally look at something sensible is the normals in the vertex shader input. I think I've mentioned before that they are normally part of mesh geometry data, along with positions and texture coordinates, so let's start with adding the new field to our vertex data. That would be here, just add the normal field like this, a new vector 3. Then here in our setup pipeline function, when we set up the vertex layout, we just add the attribute that specifies how to pass it to the shader input, just like the other ones, right? So we set the new location, format float 3, and the offset is the offset to our new field. And now we just need to actually set this field when we are uploading our vertex buffers. If you remember, we saw the notion of normals in the OBJ files, but completely ignored it before for the sake of simplicity. So let's take another look. So here I have this ambulance model, right? We have V's for vertex positions, right? And then we have this Vn, and these are exactly vertex normals, so each vertex has a normal value. then we have vertex textures, and finally we have these faces. And if you remember, the first index points to the vertex position entry, the second is texture coordinate entry, and the third one is exactly the vertex normal entry. So let's quickly add parsing for this. Let's add a normal slice to obj data. Let's add a normal index to the face entry. Let's add a new dynamic slice to collect the normals. Let's return it as well. Do not forget to destroy it, just like the other ones. And finally, let's add the parsing for that. So that would be parsed exactly like the position, except that we switch on the second character, that should be n. So let's do that. Note that we start the reading from the third character, exactly like with the VT, because after n there's a space. Finally, we need to add the index to our face parsing. So here, the third element would be normal, so we parse it exactly like this. After the next slash, we parse the normal. And maybe for the sake of clarity, we could rename our parse position function into something more generic, like parse vec3 or something. Now we just need to go here into our load obj procedure, and just like we are parsing the positions, we should also parse the normals. So let's add that. So we are just taking the value from the normal slice by using the index of face normal. And finally, if we run this, we finally see something that looks like illumination, right? If you remember, if you go into the fragment shader, we see that the light position is a bit to the right, a bit to the top, and a bit to the back. So this is roughly where we saw it. Just take another look, right? The car on the light is a bit more illuminated than the sibilance here, and there's attenuation, and it seems to be working just fine. Now we can change some intensity. Let's set the intensity to 3 or something. Maybe also set the color to red. So basically that means that the color emits the red channel, but not all the others. And we will see that everything is illuminated as red, and that is because our BRDF function dictates that all incoming irradiance is radiated back as is directly into our eye without any change. To be able to play around with this better, let's actually make the light parameters part of our game state and configure it via the inspector UI, because there's also a couple things to consider in that regard. So how do we pass this kind of global information to our fragment shader? And the answer is, well, pretty much exactly like we do here with the vertex shader via the uniform buffer object, or constant buffers if you like. So let's define one exactly like we do in our vertex shader and move our variables there. Let's call it global, because it's again something that we would like to be able to set just once per the whole frame. One important thing to keep in mind is that for fragment shader uniform buffers, we need to use the space 3 or resource set 3 as documented here in the SDL GPU create GPU shader documentation. Note that I've changed the order of fields here, and I did it on purpose to talk about something in a bit. Now let's define a mirroring structure in our Odin code. So back in game Odin, let's have something like UBO frag global and define the same fields. Then let's have the same values in our global game state. And the more I look at it, the more I think we should probably split the application globals and game globals into different structures. So maybe let's quickly add a to-do for that. But for now, let's go into our game init and initialize those fields with some starting values. So here I'm using the same values as we used before. While we are here, let's also add it to our inspector, like this. I won't dive deep into the API calls here. We just basically set some step values and min and max values. You can read about this in GUI documentation. And finally, in the game render procedure, let's push our global fragment uniform before even starting any render pass. So let's just create the UBO structure, copy the values, and push it into the slot 0 with this function push GPU fragment uniform data, exactly like we do with the vertex uniform data, just with a different function name. And that should be enough. However, if we run the game, it's not enough apparently. We only see the black screen, so that doesn't look right. changing any color data doesn't really help that, so something is wrong. And the reason for this problem is data alignment. I think I briefly mentioned it in one of the first videos that you always have to consider it and define your structure accordingly. But it was not a problem for us so far. Well, now it is. You see, graphics APIs define some requirements on how data is laid out in memory. For example, in HLSL, which of course originates from Direct3D shader model, constant buffers are made of 16-byte rows. And for the sake of efficiency, the fields shouldn't cross the row boundary. So if there's not enough space in a row, the field should be placed in the next row. So if we take a look here at our fragment shader global structure, we see that the first field is float 3, right? So it has a size of 4 by 3, so 12 bytes. Each float is 4 bytes and we have 3 floats, which will leave only 4 bytes of empty space in the row. And the next field is also float 3, right, light color. So that's 12 bytes, which is more than the space left in the row. So it is expected to be in the next row, starting at offset 16 and not 12. Now, our Odin structure for this is just a normal structure that has nothing to do with GPU constant buffer rows. And hence, it uses the standard alignment rules. Basically, this means that the light color field here will be placed right after light position field, so at offset 12. And we can in fact actually print those offsets to verify that. For example, here we can go in main init and do some logging. So here's the logging. We are just using the size of and offset of built-in functions. And we see that the size of the structure is 28 byte and the offset of light color is indeed 12 bytes and not 16 as required by shader. So that's a problem. And the most straightforward solution here, in my opinion, is to just use explicit packing on the Odin side. And for that, we can add the pack directive to the structure, like this, so right after the struct keyword. And then we can add explicit padding fields as required. So here we just need one. For example, like this. We could use underscore as a kind of ignored name. You could also go more explicit like this, so 4 bytes specifically. But I think F32 is also quite readable because it says 32 bits, right? So now our data is laid out correctly and we can see the correct results. We can move the light, right, with different positions. We can change its color maybe to something like this. We can change its intensity. So that seems to work pretty well. Probably we should draw something where the light is so we can see its origin, but let's do it in one of the next videos. And just a couple more words on the alignment. First, you can use this amazing tool. It's on this website. I will of course add a link to that. That helps you visualize how the data is packed. So you can see the padding here, 4 bytes exactly, right? And if we would move, for example, float light intensity up, then we would see that it would fill this padding space and would be packed at the offset 12. So something like this is interesting. And then also the SDL documentation mentions that the data must respect the STD 140 layout convention, which means that the vector types must be aligned to 16 bytes. This is a similar requirement as we just seen, except that it also requires that fields like float 3, float 4, they must always start at an offset that is a multiple of 16, which I believe is not a requirement in HLSL and Direct3D. We can actually try and break that. For example, we could put intensity first and then the light position, so it fills the rest of the row. So it would look like this. And this supposedly is not supported by the STD 140. However, if we run this, that seems to work just fine. Right. And I briefly looked into the generated SPRV shaders to see why, and it seems that our compiled shaders have this scalar layout used, which is this GLSL extension introduced back in 2018. Now, I don't really know how well it is supported, so maybe it's just safer to follow the STD 140 rule and make sure that your vector fields are always aligned to 16 bytes. Alright. I think that's enough for this video. We have the radiance from our light reflected directly into our view, and the next time we'll work on this BRDF function to make the reflection more interesting. So stay tuned.